Okay, hello everyone. So there's been some questions on Piazza and at office hours and so on about these kind of different error terms that we saw in the evaluation chapter of the different predictors. And so on top of this video, I actually wrote up a new section, so section 7.6 in the course notes, that explains kind of these different errors and what they're affected by in a kind of one-page summary. But I thought I'd also go over it here. Okay, so the main thing to note is that we are trying to minimize this object here. It's like the expected loss averaged over data sets. And in the evaluation chapter, what we learned is that we can break this thing up into two different error decompositions. The first one is this guy here, and it's broken up into this estimation, approximation, and irreducible error. The second one is this guy here, and it's broken up into variance, bias, and irreducible error. Okay. The first thing to notice is that, like, what are these different predictors and all these things? And there's really four different predictors. Okay. There's this f hat, which is the actual predictor you're going to output with something like ERM. Okay, so you're going to minimize the estimated loss, that's L hat. You're going to pick the best f in your function class. Okay, then there's these two other predictors. There's the f star, which is going to be in this, considering the same function class as what your like ERM predictor, ERM learner would be looking at, except now it's actually minimizing the true expected loss. So this is the difference between the two. And then there's this f bar predictor, which is called the average predictor or the expected predictor. And this is just the average of the predictor your ERM learner would output for a fixed feature X, okay? This is like you fix a feature X, and then you consider what's the different predictors you'd output for different data sets, and this is just the one, the average predictor. Okay, so we've kind of seen some plots and so on about this. This is somehow related to f star in a certain setting, and we'll see that too. And then there's f base, which is just simply the best possible predictor you could imagine to ever output. This really minimizes the expected loss, which is what you really want to minimize, and it's considering all possible functions, so no restriction, no function class here. Okay. So then we talked about these different errors and how to minimize them and what affects what and so on and so on. And so I wanted to just start with the simplest one, which is this irreducible error. So it comes up in both decompositions. Okay. And the way to decrease this is the same in both cases, and in general you usually will not be able to decrease it because the way to decrease it is quite challenging. And the way to decrease this is to, and I guess I write here, is to gather more informative features. This would be something like if you want to predict house prices and you only have, let's say, the number of rooms in the house in your features, well then the only way to reduce this irreducible error would then be to go out and gather more information about the houses you already have. And this more information, more informative features would be something like maybe the number of people that live in the house, maybe where the house is located, and so on and so on. And this is usually very challenging to gather or like impossible, and so you say this is the irreducible error. But if you can gather more informative features, you can add new dimensions to your features, you can decrease this object. Okay, so that's all I have to say about that. The other ones, these other four, estimation error, approximation error, variance, and bias, I've made a nice table here, hopefully it's nice and helpful, to discuss about what different things you can do to change them. Okay, and really there's only three objects that we can modify to affect these four pieces of error. Those three objects are the size of the dataset n, the degree of the polynomial function class p, there's this polynomial function class, right, f of p, and then there's the regularization parameter lambda. Okay, so let's go down each of these columns and discuss what happens when we modify each one of these three kind of objects or parameters. Okay, so changing n, and we're going to consider the case where we increase n. It turns out to have a very obvious and nice effect, and that is if you increase n, estimation error and variance will decrease, or stay the same. So, okay, one important note, all these columns that say, or all these cells that say increase or decreasing, they should all be considered as increasing or equal to, or like decreasing or equal to, or like increasing or stays constant, doesn't change, or like decreasing and doesn't change. Okay. So, yes, estimation error, variance, both of these decrease with n. We discussed in the course why this happens. I'm not going to go into too much detail like right now. But yes, these depend on n and these change. The other two, approximation error and bias, they do not change if you change n. Okay, that's the effect of n. And from this, you can draw the obvious conclusion that if you increase n, you simply will always reduce your error. There's no harm in increasing n. You should always increase n if you can. Okay, so like basically this is like always good to do. Increase n. Okay, and then the other two columns are where we get a little bit more interesting behavior because there's some trade-offs. Okay, so polynomial degree p. Changing this changes your function class. And here we consider the case where we fix the regularization. So we want to talk about how polynomial degree changes things without like having any effective regularization. So set regularization to 0. And then we're going to do the other case in this column, which is we want to study how regularization affects things. And to do this, it's helpful to consider a very complicated function class, so polynomials of degree 10. And we'll come back to this in a second. So let's study this column. So this is just changing the function class. Okay, and the effect of this with regularization equals 0, the first thing to note is that what was mentioned in class is that in this case, estimation error and variance are actually identical, they're equal, and so is the bias and the approximation error in this case, okay? And that's because this f bar turns out to equal f star. Okay, it turns out the average or the expected predictor is actually exactly f star. Okay, so then the behaviors are literally identical. So what happens is that the estimation error is going to increase, right? So this is this cell, increase as p increases. And this is because the function class has gotten very, very large, okay? Then there's approximation error, which is going to decrease. And the reason it's decreasing is you can clearly see f star is going to decrease if f is bigger and bigger, meaning you can find a better minimizer to the expected loss. Until the point when it reaches f base. And why is, like, what does this mean until this point? What it means is if we look at the approximation error, we see that this will be 0, so this will be 0 when f star equals f base. When will f star equal f base? Well, at the point that this function class f will contain f base. Okay, so we're varying this function class by changing p. At some point, p will be large enough such that it contains f base, and at that point, the approximation error will be 0, and there it just simply will not change anymore. You can't decrease further than 0. Okay, so that's like an important case. So if f base is very, very simple, increasing p really won't change anything because you already have a complicated enough function class to represent the best possible function. Okay, and so same behavior with variance. Variance increases with p, bias decreases. Okay. Now it becomes maybe the most kind of interesting and complicated setting, which is what the regularization parameter does to all these. Okay. So here we fix a complicated function class, so p equals 10, so these are polynomials of degree 10 or less. And now we're going to consider how does the regularization parameter affect things. So roughly speaking, we said like when regularization, or not even right, just like precisely speaking, when lambda equals 0, which is the case we saw over here, we have no regularization and the function class, or like we really are just using the exact same estimated loss as we've been using before. There's no regularization term. You don't get penalized at all for having your weights being large. Then when you make lambda larger and larger, what you end up is you end up penalizing large weights, which we said can be thought of as forcing your learner to pick predictors that are simple. Okay. Then there was the simple cases, which is variance and bias. And this is when variance and bias kind of shine in the regularization case. So when we talk about regularization, often people will talk about variance and bias because these have very nice effects, which we'll talk about in a second, while estimation and approximation error don't really follow very nice trends with changing lambda. Okay, so what happens when we change lambda? When we decrease lambda, we're outputting predictors that are more complex. That means that the variance, which talks about how much does your predictor change relative to the expected predictor over data sets, right? So if you can output more complicated predictors, this can change much more, or it can vary more, so your variance goes up. Okay? Oh, this is totally incorrect. Okay, well, I'm going to correct this in the notes, and I will write this here, since I do not want to re-record. So this should say that the variance increases if you decrease lambda. You're going to output more complicated predictors. And this should say that it decreases. Okay, this is good to catch. Right, so variance is going to increase if we decrease lambda. We're outputting more complicated predictors. And the bias is going to decrease. Why? Well, the bias is measuring how far is the expected predictor relative to f base. If we can output more complicated predictors, then we can get something closer and closer to f base. Okay, so these two should make sense. And now come the more maybe like kind of edge cases or interesting ones, which is how does approximation and estimation error get affected by things? So the approximation error, if we look at it, is a measurement between the expected loss of f star and f base. F base is, of course, not going to change with lambda or p or whatever. That has no effect. But f star has, like, what is f star changed by? F star will be affected by the function class. And changing lambda does not change the function class. The function class is fixed to p equal to 10, so polynomials of degree 10. So approximation error simply does not change. That's unchanged. Okay, and then finally we have the last case, which is this estimation error. And this is actually a much more complicated case. And so here I wrote it's unclear because there's kind of two opposing forces. And so this will not be kind of asked in any exams or questions just because it's kind of complicated to study. Okay, so what happens, just like roughly speaking, with this estimation error? Well, if we look at the estimation error, clearly f star is not getting affected. We said this is just fixed. It doesn't change with lambda. So what's left is this term. But this term has some like opposing forces here with lambda changing. Okay, so why is that the case? Well, when lambda changes, we're allowed to now the predictor that's going to be output. Okay, so when lambda decreases, the predictor being output by the learner is going to be more complicated, right? That allows f hat to be closer to f star. You can think of that as sort of like allowing you to pick more complex or more functions from your function class. And so this f hat will be getting closer to f star. However, the problem will become that this, although f hat here is getting closer to f star, it's going to be able to vary a lot more between data sets. And so this will differ quite a lot, or it can differ much more because it's going to vary across data sets. And so there's these two opposing things, which is if you decrease lambda, you allow more complicated functions to be output. F hat for a specific data set can be much closer to f star. But across data sets, which is what this expectation will measure, it can be quite different and it can vary more if you allow more complicated predictors. So anyways, this case is unclear because it's not clear which of the forces is dominating here. Okay, so that's all I had to say about this. There's a bit of a discussion as well in the course notes about these different cases. And there's one last note I wanted to make, which is we occasionally see plots where we talk about how close two predictors are, and this may be confusing, even though we kind of discussed this in the assignments, especially the coding ones, and we saw visually that changing changing the error, making, let's say, like the approximation error smaller, we could then plot the two predictors and see that they themselves are getting closer to each other. Okay, and it may not be obvious why this is happening sometimes, and I just want to kind of explain exactly what we should assume in this course and so on. So there's this, let's look at one of the errors. So approximation error. Approximation error is measuring how close kind of f star is to f base, but not directly, but through this expected loss. So there's some function being applied, and then it compares the function, like expected loss, it compares f star and f base, but through this function, the expected loss. And so the question is kind of like, if this is small, does that really imply that f star and f base is close? Okay. And so in general, or you can like find some edge cases for specific expected losses and under specific distributions where this might not be the case, okay? However, in general, or like usually, this is true, okay? So like the answer is most of the time. Okay, so most of the time, these two this being small will really imply that the corresponding functions being plugged into the expected and the expected losses are themselves close. And what does it mean for two functions to be close in the way I'm speaking here? It means that if you look at every single feature vector in the set of feature vectors, plug that into each one of these functions, that gives you a number. These numbers are close for all possible features, all possible feature vectors, okay? And visually, this would mean that if you plotted the two, you really would see that they are close together in the sense that like maybe this is f base, and then if we plot f star, let's say in purple, then we would find that they are close for all values of x, right? So this is x here, this is x, and we would really find that like at every point they are quite close together, okay? And so in questions, as you had seen on the midterm, the questions will say things such as, is it likely or would you usually expect that these two should be close from a plot or something like this? So I just wanted to clarify this as well. Okay. I hope this helps, and if there's any questions further about this, please ask on Piazza, and yeah, have a good day, everyone.